Okay, thank you very much. And it's a great pleasure to be here in Budapest and also be invited to give a lecture series. So I want to speak about graph limits and applications to group theory. And so since I'm originally interested in the group theory part of this, I want to start explaining two famous open problems in group theory, which are not only interesting from the point of view of group theory, but actually have been motivated by questions from algebraic topology. But in the end, they are interesting if you just want to understand the structure of groups and the whole variety of groups. And the, interesting part that is relevant for us in this lecture series is that they can be solved if you understand enough about graph limits and can use the knowledge that a certain group has a certain approximation property. So that's something that we want to come later to. And so the first conjecture that I want to state is very easy to state. And that's the following. So let gamma be a group and K be a field, and then take two elements, A and B, in the group ring of gamma with coefficients in this field K. So that's a ring, so that's just as a vector space has basis given by gamma, you extend the multiplication, so I think everybody has seen the group ring. And so let these be two elements which satisfy that A times B is equal to the identity in this ring, which is just the identity in the group. Then the conjecture says that in this situation, also B times A is equal to the identity. Right? A very easy ring theoretic property that this ring can have. And in fact, in many examples, we know that this is true. And I will later explain more about the status of this conjecture. But anyway, that's a very fundamental problem to decide whether this ring has this property or doesn't. And as I said, it's actually originally came up also, or is actually also related to questions in algebraic topology and in the computation of the K-theory of this ring, which is very relevant in the classification of manifolds. So it's not just a problem about groups itself, but has interesting applications. And the second conjecture is a little bit more complicated to state, but let me first give you a definition. So again, let gamma be a group, and let G1 up to Gn be elements in the group, and you also have numbers, epsilon 1 up to epsilon n, these are integers in fact. Then you can ask the following question, or first of all, that's the definition. We say that the equation W of t equal to G1 t to the epsilon 1 up to Gn t to the epsilon n has a solution, in gamma, right? That's easy if there exists a t which solves this equation. If there exists a t in gamma such that W of t, if you insert it, right? So maybe I should write t prime so that we don't confuse it with this unknown. So if there exists something that you can plug into this equation, and if you multiply out the product, then you get the identity. Right, then you would actually say that you can solve it in gamma, and you can solve it over gamma if there exists a group extension lambda and some element in t prime which lies in this bigger group lambda, so that W of t prime is equal to the neutral element. Can you read this here, this line? Yes. Let's do it here. Not really, okay. Now you can read it. Okay. So you say you can solve it over gamma if you can extend the cube. So that's actually completely similar to a very fundamental question in algebra, where you start with a field and you want to solve some algebraic equation, right? Sometimes you can solve it in the field, and sometimes you can extend the field to a bigger field and you solve it in the bigger field, right? So here we ask a very similar question in the category of cubes, and the question is, does such a solution over gamma always exist, right? And a little bit of thought reveals that this is of course not the case, because we can cook up some nasty equations. So for example, if we take this equation A, T, B, E, T inverse, and if the order of A is different from the order of B, right, and both, let's say, finite and also prime to each other, let's say, then there exists no solution over gamma, right? Because A and B just cannot become conjugated in a bigger cube because they have a different order, right? So you don't need any assumption apart from the assumption that it's actually different, right? But this is a very special equation, because that's somehow what you observe, is that the sum of the exponents in T adds up to 0. That's like a singular case which you should take special care of, right? So in the conjecture 2 is that if the sum of these epsilon i's is not 0, then there exists a solution over gamma, right? So there exists some extension of this cube gamma in which you can solve this equation, right? It's a very fundamental property, right? It's as fundamental as the existence of field extensions in some sense, but it's only a conjecture. And well, the problem with this conjecture is, like with all conjectures about cubes, is that you want something that holds for all cubes, right? And that's very difficult because you don't know how to start, right? A cube in general is hard to understand if you don't have any more assumptions. And so the weakest assumption that is sufficient to prove this conjecture currently is some approximation assumption on the cube, which is very much related to this theory of graph limits. And so I will explain this approximation property and then also explain how you prove this conjecture for this class of cubes. Okay, so that's my motivation. So I hope it's also a motivation for you to start with this study of graph limits. So the way it's done in this lecture, and then that's a bit different from the way that we have seen in the first lecture, where the emphasis was on dense graphs. So from now on, I will always assume that there is some fixed integer d, and all the graphs that I study will have a maximum degree equal to d. Right? From now on, all graphs have maximum degree d, where d is some fixed integer. And so of course it might change with the problem that you study, but it's always, so in any statement it will be fixed, and I will not mention it anymore because I would have to mention it every time. Yes? Yeah, but the plan was to do this later when I prove them, but I can also do it now if you like. So this is known if the characteristic of k is equal to 0, but that's also not obvious, right? So it's also not obvious. So you have to get into the study of von Neumann algebras a little bit, and if you look at this just as a combinatorial problem on the cube, then you don't get anywhere. So you really have to use some more global approach to this problem, as far as I can tell. And in the case when the characteristic is p, then there's the result by Gabor Edek and Sabo, which have proved that if the cube is Sopic, a concept that I will define, it's related to these graph limits, then it's true for any field. Right, but we don't know whether every group is Sopic, but it's definitely a large class of groups. And here it's a bit similar, so at least for Sopic groups this is known. Yeah, it's known for a potentially larger class, but Sopic groups is definitely already a good class of groups. So all the graphs that I want to study have maximum degree D. And okay, so let's consider a sequence of graphs, and well, try to find some reasonable notion of convergence if these graphs have a maximum degree D, right? And before we have looked at the homomorphism density, right, which was defined to be the number of homomorphisms from F to G, F some fixed finite graph, divided by the number of all possible maps on the vertices. And well, and that's of course not going to work, because if, let's say, F is connected, then this will grow, right? If I put an I here, this will grow linear in the size of the vertex set. And so if you divide by this number, then everything will tend to 0 unless basically F has no edges at all, right? In that case, well, you get 1, right, which is also not interesting. Okay, so the right thing to do is to take a different normalization and restrict the class of Fs. So you take you can take that as a definition, right? So we say that GI is convergent by definition if for all F which are connected, this modified density, you divide the number of homomorphisms just by the size of the vertex set of G, if this converges. Right, so that's a modification, it's a different normalization, but for the bounded degree case, that's just the right thing. Right, and now so far we have done basically nothing but to write down some obvious thing that we want to have converge if we speak about a convergent graph sequence. And the interesting part really starts if we want to develop this second picture, which is more analytic. Right, in the first talk, this picture was described by the space of graph horns and this cut distance, and then you have to show that these define the same topologies. And so surprisingly, this study of bounded degree graphs leads us in a completely different direction. So the limit object is of a completely different nature in some sense. And what I want to describe now is a good space on which you can study the limits of such convergent graph sequences, and also, say something about graph sequences by studying the limit object. Okay, so in order to do this, I have to introduce a little bit of terminology. And so first of all, I want to study the space G. This is the topological space of rooted graphs. So I will typically write them as a pair, G, 0. So G is the graph, 0 is the root. And so I omit the D. The D is always fixed, right? So these graphs have all maximum degree D. Right, and if I say topological space, I have to say which topology I'm talking about. And I will describe a metric on this space, and the topology is induced by the metric. But the metric is in some sense non-canonical, right? So the metric is, there are choices just as, right, in the choice of the metric that we have seen in the first talk. So the metric is defined as follows. If you have two graphs, then you define them, their difference in the space of rooted graphs to be the infimum of 1 divided by 2 to the n, such that there exists an isomorphism. In fact, it's a rooted isomorphism. So an isomorphism which preserves the root of the ball of radius r around the root in the one graph and the ball of radius r around the root in the other graph. Right? So let me write isomorphism here. Right? This is the ball. Yeah, sorry, this is ball of radius r around the root 0. Right, and it's a very easy exercise compactness argument to see that if this infimum is actually 0, so if this exists basically for all r, then the graphs have to be isomorphic. So this is really defining a metric. Yes. Okay, so that's important. I mean, it's a topological space. Sorry, these should be connected graphs. And so if the metric distance is equal to 0, then actually these graphs are isomorphic, and so I have to make it even more precise, this definition that I said. I actually speak about isomorphism classes of connected rooted graphs. Right. And these isomorphism classes will be rooted isomorphism classes. Okay, so anyway, that's a very natural definition. So you call two graphs close to each other if looking around the root, they really look the same for a very long time. Right, so. And now what you can do in order to study, let's say a finite graph, like one graph in this graph sequence, is to associate to it a probability measure on this space of rooted graphs, and that goes as follows. So let G be a finite graph, so without preferred root. Then we can define mu of G. This is a probability measure on this space capital G that I have defined. It's a probability measure, and it's defined as follows. Is you take a convex combination over all the vertices in G. So you sum over the Dirac measure of G rooted at V. Okay, so let's say V runs through vertices, so maybe in order to make this definition in this form, I should also assume that this graph is connected. I mean, it doesn't really matter for this definition. But, so that's the definition, right? So you choose a root V in G at random, uniformly, and you sum over all the choices. So, I mean, that's how you describe this uniform random choice as a probability measure on the space of rooted graphs. Right, on the space, I mean, in the space of probability measures, there's a very natural notion of convergence, which is well studied, which is the weak star convergence. And so let me define that. So we say that the sequence mu n, so mu n is a probability measure. Well, in fact, in any compact space, but let's take this space G. That this is weak star convergent. Well, if for all continuous functions on this space, on the space of rooted graphs, the integrals will converge, right? So the integrals of, well, you can integrate this function with respect to the measure un, so this will converge, right, for any continuous function. Okay, so that's a very reasonable notion of convergence, and it is well known that the space of probability measures with respect to this notion of convergence is a compact space, right? So you have found a nice space in which limits have a high chance to exist, and now the theorem, which is in some sense the analog of the theorem that we have seen in the first course today, is the following. So the sequence GN n converges if and only if these measures that you associate to these finite graphs converge. Right, and in this case we say that the sequence Gn is Benjamini Schramm convergent, because the Benjamini and Schramm have, well, studied this notion a lot and have introduced a lot of concepts in this area. Right, so we call this Benjamini Schramm convergent if this is the case. Right, so that's very nice. And so we know now what the limit is, right? The limit, at least if we follow this philosophy, the limit itself is a probability measure on the space of rooted graphs, and that's how we should think of it. Right, and so the interesting part now, the interesting next step is to identify the crucial properties of those probability measures that arise as limits of finite graphs, right? Because of course not every probability measure can have this property, and I can show you some simple consequences of being a limit of finite graphs, which are not satisfied by all the probability measures. Okay, so being weakly convergent means that you can integrate every continuous function, and then you have convergence of the resulting sequence. And so this space G, space of rooted graphs, is a totally disconnected space. So it has tons of continuous functions which are characteristic functions and which detect properties of the graph. So you can now speak about, so let U be a probability measure on this space. You can, for example, speak about the probability, let me write it like this, that some rooted graph, so for example, let's take this graph. So here is the preferred root with a little box. So you can consider this probability, right? So what is it? So it's the probability that seen from the root here at distance 1, there's one triangle, right? You can study that. And so for any finite graph, it's very easy to see that the probability that you see this picture is just the same, because you just count basically the same structure in a different way, right? You now count, here you counted basically vertices with a triangle at distance 1, and here you count vertices which are at a triangle and have an additional edge, right? So that's a priori a different counting problem. Well, it doesn't matter, right? So if you just want that this is a subgraph, then you are basically in this situation, right? Or maybe you have loops and it's even more complicated. But I mean, whatever you want. So it will always be the case that you can change the root in such probabilities, and the number will obviously not change because it's just a different way to count the same number of configurations in a finite graph, right? So this will be the same if mu is equal to mu g for g finite. Right, and so in general, we would like to formulate, I mean, of course, if that holds for any finite graph, then it will go to the limit, right? For any measure and the limit, the same will be true. Right, and we want to formulate an abstract kind of condition on this probability measure, which captures this phenomenon that we have encountered in this simple example. Right, and the abstract way to formulate it is to look at basically graphs which have two roots, and you compare the two measures that you get by forgetting one of the roots, right? So abstractly you do it as follows. So let G sharp be the space of connected graphs with two roots, O1 and little o2, then this space G sharp, it comes with two maps to G, and one is forgetting the second root, that's pi1, and one is forgetting the first root, that's pi2, right? So there are two natural maps, and you can use these maps to lift the measure that you have on G to a measure on this space G sharp. Okay, let me explain you how that goes. So first of all, the space G sharp itself is again a very nice space. It's a locally compact space. It's not compact anymore. And these projections are obviously continuous. And if you look at it, so the fiber over each point in G with respect to pi1 or pi2 is obviously countable, right? Because the fiber over pi1 just amounts of choosing the second root, right? That's there are obviously only countably many choices for that. The topology, well, it's again so you take these two roots and you look at, I mean, they are only at distance r, and then you look at some neighborhood around these roots and you define a metric very similar to the metric that we have seen for G. Okay, so how do you get measures on G sharp? So let B in G sharp be a Borel subset. Then we define mu1 of B. So we want to define a measure on G sharp, so we should assign a number to B. And so how do we do this? We integrate over the space G the inverse image of X. So let me first write down this formula and then explain what it means. So that's G0, and you integrate with respect to mu. Right? So mu is our measure. So mu is a probability measure on G, and we lift it to a probability measure on G sharp basically by, I mean, locally taking a product with respect to with the counting measure in this fiber direction. So if the fiber is countable, then you can just do that, right? You count how many times you hit the fiber. So that's the inverse image under pi1 of G, 0 is just the same graph where you add a second root, right, in some way, right? So this inverse image is just a set of all graphs which have as graph G and as the first root this O, right? And you count how many times, this is a countable set, you lie inside B, so this is the cardinality, and then you integrate that over the measure mu. Right, and obviously you can do this in a very symmetric way, so let me just write I here for I equal 1 and 2. And so the definition that we are after is the following. So mu is called unimodular if mu1 is equal to mu2. Right, so that's the definition. Right, and that exactly captures this phenomenon that we have observed, that this double counting always gives the same number. So if you have two possible choices of the root, then it doesn't really matter whether we concentrate on the first root or concentrate on the second root. We just have to count what we get. Right, and it's a very simple argument, well, similar to this observation essentially, that if such a measure is a limit of measures coming from finite graphs, then the measure that you get is unimodular. Right? So those measures which have this property of being limits of finite graphs, they also have a name. Definition: if mu is equal to the limit as n tends to infinity of the measure mu gn for a sequence gn of finite graphs, then mu is called Sopic. Right. And so, summarizing this observation that I just made, if mu is Sopic, then this mu is also unimodular. Right. So this is, I mean, I didn't prove it, but I showed you that. I mean, this is of course a much more abstract formulation here, but it's, I mean, if you think about how to formalize this picture that we have seen up there, then it's exactly this measure that you should study. And of course you could stick with this formulation, right? I mean, if you have this property for all finite configurations and for all pairs of roots, this identity, that's exactly the same condition. But in order to say more about unimodular measures, you really should study this measures, I mean, this now uniquely defined measure on G sharp, because it's a measurable equivalence relation, and there are a lot of things from the ergodic theory that you can then use to study this situation. Okay, so there's a conjecture in this context. And the conjecture, I think, is due to Aldous and Lyons. So I think it was also a theorem at some point, but it's a conjecture at the moment. So the theorem is that the inverse implication is also true. So it's if it's unimodular, then it's also, then the measure is also Sopic. Right, okay, so, I mean, the way I presented it, maybe this does not sound so interesting, but this really has a lot of very interesting implications, and it sort of fits with with philosophy very well, that some finiteness conditions which are more intrinsic, so the approximation by finite structures, that this should be equivalent, as it is in many cases, with a finiteness condition which is more of this type, that this mu1 is equal to mu2. So we have also seen this, I mean, at least in some way, in this first conjecture that I made about properties of elements in the Coop ring, where you also have this ring theoretic finiteness condition, which you want to study. And so if you have such an implication, then you can really relate it to some properties that arise because you are a limit of finite structures, and that's very useful. Okay, so let me give you one more example in order to see that there are many cases where this conjecture would apply where you don't know whether it's true. So let me provide you a large source of unimodular measures. And so now I'm getting back to group theory. So let gamma be a finitely generated group, and S in gamma be a finite symmetric, right? So this means that S is equal to its inverse as a set, finite symmetric generating set. Then we define the decay graph of gamma with respect to S. So that's the graph which has vertex set equal to gamma, and vertex edge set equal to gamma times S, where so gamma G comma S is considered to be an edge between G and G times S. Okay, that's a graph, and so by its basically very construction, it has a very large automorphism group, so the group gamma acts on this graph. So the automorphism group of this graph is transitive on the vertex set. You can just shift on the left by gamma, and so there's basically exactly one rooted graph that you can possibly associate to this object, even though it doesn't have a natural root if you forget about the neutral element. So if you just look at this as a gamma space, it doesn't have a natural root. But since anyway the automorphism group is transitive, you can look at the Dirac measure of the Cayley graph of gamma with respect to S, and that is a unimodular unimodular measure on this space of rooted graphs. Right. So that's not entirely obvious, but I don't want to prove it at the moment. Okay, so that's good. So that's a large class of examples, and for those, for a general group, a general finitely generated group, it's not known whether this measure that you get there is Sopic. So that would in fact have a lot of interesting applications. So now you might think maybe I can take an arbitrary graph which has a very large automorphism group and do the same thing, but that's also an example that one should keep in mind. That's not possible. So that goes as follows. You start with a 3-valent tree. Infinite. And you pick a direction, you pick a point at infinity, so let's pick some point in this tree at infinity, and this allows you to direct all the edges away from infinity. Right, so that's how this goes. And so you can now think of this basically, well, this, I mean, it's called the grandfather graph that is constructed now. I mean, you think of this as basically the, so how is it, so these are, so if this is infinity, then this is the father of these two children. So every vertex has basically, I mean, if I would have drawn it correctly, would have exactly two children. And so the simplified model for, how do you say this in English? I don't know. It doesn't matter. So anyway, you introduce new edges which connect the grandfather to the grandson, right? So that would add more edges here, like this. So that's the so-called the grandfather graph. So the white edges and the red edges together. And the resulting graph is a vertex transitive graph. So you get basically one choice of a root by just setting it here if you want. But the corresponding measure is not unimodular, and the unimodularity exactly fails because, well, one father has two sons, but only one father himself. So that asymmetry, which is encoded in the graph structure here, prevents this graph from being unimodular. And I think this is a good exercise to explain. Right, so if this graph is called G, some arbitrary root, explain why this graph does not yield a unimodular measure on the space of rooted graphs. Right, and so in particular, it cannot be a Cayley graph, for example. Okay. So now we have already seen what it means to have a convergent sequence of finite graphs, and we have seen this concept of unimodularity. We have seen this large class of examples of Cayley graphs, and I now want to focus actually on this class of Cayley graphs and study in more detail what it means that the Cayley graph yields a Sopic measure on this space of rooted graphs. Right, and in order to do this, one has to modify the framework just a little bit, but it's not a serious modification. And this goes as follows. So let gamma be a finitely generated group, and S such a symmetric finite generating set. Then we consider a kind of enriched Cayley graph. So I will also denote it by this, where we also remember, I mean, we consider this set of edges, they are not just as a set, but we actually remember the name of the label. Yeah? So this is now considered to be a directed right, so let's say edge labeled graph, and the edge labels are exactly from this set S, right? And the edge that corresponds to G comma S exactly carries the label S. And so if you, what? Oh yes, I'm Sorry. And so exactly. So the edge corresponding to G comma S exactly carries the label S. So if you know the directed and edge labeled Cayley graph, you can immediately reconstruct the coupe by just looking at how these labels combine, right? So if you, just look at an example. If you have the neutral element, you don't even know that it's the neutral element. Then let's say you have a directed edge S, and then you have a directed edge S prime leading you to some other coupe element H, and then maybe another edge leads you back. Then you can immediately read off that S times S prime times S double prime must be the identity in the coupe, right? And if you know all these relations, and you know them all because they are all encoded in the graph, then you can obviously reconstruct the coupe just from this picture. And that's not the case. That's not the case if you just know the underlying graph, right? There are many, not many, but there are examples of coupes which are different, but they have isomorphic Cayley graphs, right? So this is really more information. And so it's adding this direction and the labeling. But for our study of the measures, this doesn't make any difference, right? So you can just now define an extended, right? Maybe I add a little s here, space GS of connected, directed, S-labeled S-labeled graphs, and that's just adding a little bit more of structure to your object, but the entire study that I described, so that every finite graph leads to a probability measure, and then you can study these measures from 2 points of view. You can just look at the analog of these homomorphism densities, or you can look at the weak convergence on the space GS of probability measures. That's all the same, right? So we can now define, following this analogy, what it means for a coupe to be Sopic. So a coupe gamma is Sopic, and let's for the moment assume that it is also finitely generated, just to simplify the matters a little bit, that this really doesn't matter in the end. So if there exists a finite generating set such that the measure, the Dirac measure, right, this is a probability measure. So the Dirac measure corresponding to the Cayley graph with directed edges and labeled edges, so it's a probability measure on the space GS, is a limit, or actually I can just say is Sopic, because I've already defined what Sopic means. Right, and so the first question is, does it really depend on the generating set? And the answer is, it doesn't depend on the generating set. Right, if true for 1s, then for all generating sets. Was there a question? Oh, yeah, okay. So if in a few hours, when you read through the notes that you took, there's some G at some point, then it must be a gamma. So it's just that we have overlooked it. Okay, that's very nice. And in order to work with this definition, I want to explain a few equivalent notions. And maybe we can first think for just a little moment what this definition actually means. Right, so what it means is that this Cayley graph, so its properties, can be understood by understanding a sequence of finite graphs which in this space of probability measures converges to the Dirac measure at this graph. And what that exactly means is that on more and more vertices and larger radii around these vertices, these finite graphs will actually look like this graph. So if in the simplest case this graph here, for example, you start with the free group, so you have some, let's say, free group on two generators, you have some four-valent infinite tree, then the sequence of finite graphs, around most of the edges, more and more of the vertices, you don't see any loops, right? And in addition, also the labeling has to fit, right? In addition, also you have this labeling by letters A, B, A inverse, B inverse, and also this labeling somehow has to be compatible. So let's look at some examples where this can actually be done before I continue with the other definition. Right, so let's look at the example Z squared and the elements 0, plus minus 1, and plus minus 1. 0, this is the, right, so this is our set S. Right, then if you draw this Cayley graph, then you have here these labeled and directed edges, and there's a very brutal operation that allows you to define a finite graph, which sequence of finite graphs, in fact, which will converge to this infinite graph, is just by cutting out a large, well, window of, let's say, square size. Right, so that's window of size n, and then it's an easy exercise is that the labeled graph that you obtain by just cutting down this picture, let's just write Cayley graph of Z squared with respect to x, and then cut down to this box of, let's say, size n. So this measure converges to the Dirac measure of the Cayley graph of Z squared with generating set S. Right, so Z squared is definitely then a Sopic group. Right, and if you have seen this picture and you know the definition of amenability, then exactly the same argument works for any amenable group. Right, so observation, remark, if gamma is amenable, then gamma is also Sopic. Right, that's one large class of Sopic groups, and another large class of Sopic groups, which is in some sense kind of complementary to this class of amenable groups, is the class of residually finite groups. So I don't know whether I should define all these notions. So who knows what a residually finite group is? Okay. This also. Right? Who wants to see the definition of an amenable group? Okay, that's definitely you. Okay, so let's add it. So gamma is amenable. So let's assume that again, gamma is finitely generated. That makes it a little bit easier to state. Be finitely generated, and this S, this set S, as above. Then gamma is amenable, a notion which was defined by the Hungarian mathematician John von Neumann, as one should say. Gamma amenable if there exists a sequence. So that characterization is due to the Danish mathematician Völner. So if there exists a sequence of finite subsets, such that if you take the size, so now I have defined the Cayley graph as acting on the left, so I take f, so the size of the set f times s divided by the size of f, right? So there's this fn times s. Okay, sorry, I have to modify it just a little bit. I take the union with fn, right? So I take fn union with fn times s. I divide the size of this set by fn, size of fn. So this should tend to 1. Right, so definitely this set up here is larger, so the problem is that you get it small enough, this set. Right, so what you should think of is that adding s to fn does not make fn really very much larger than it already was. Right, and we exactly see this phenomenon in this picture. If this square is large, then adding plus minus 1 to it does not make it really very much larger, because the size it already had was n square, and then you add a little boundary which is only linear in n, so definitely this fraction will tend to 1. Right, so that's the definition that I want to use, and from this definition, if you have done this exercise, then you will also be able to show that the amenable groups are Sopic, because what do? Instead of cutting down to these squares, you cut down to these sets Fn, and these are finite sets, and the resulting object will converge to the Dirac measure of the Cayley graph of the whole group. No, I don't. I can, but it does not matter. And so the other definition of residual finiteness is the following. So gamma is called residually finite if for all f in gamma finite subsets there exists a finite quotient gamma onto lambda, so it's a finite quotient of gamma called lambda, and so this surjection is called phi, let's say, such that phi, even though it's of course not injective, right? Gamma is typically an infinite group, have a huge kernel if it surjects onto a finite group, but on F, this map is injective. Right, so what does it mean? That means that any phenomenon whatsoever that you observe in gamma, as long as it is concentrated on some finite set, you will also observe the same thing in some finite group. Right, and that's a very strong statement. So there are a lot of things on finite groups that you prove by induction or by whatever method that you have available for finite groups, but still the same proof is not available for infinite groups in general. So maybe sometimes it actually fails for an infinite group, and then this infinite group cannot be residually finite, just because there's something going on which cannot happen in a finite group. And so I want to end by just saying that that's actually also only a lemma. If gamma is residually finite, then gamma is also Sopic. And the reason is that you you choose some sequence of finite quotients which eventually sees more and more of your infinite group, and then the sequence of Cayley graphs of these finite quotients will converge to the Cayley graph of this infinite group. So the Dirac measure of the Cayley graph of some sequence of finite quotients, this will converge to the Cayley graph of the group with its original generating set. And so hence gamma is Sopic if it was residually finite. Right, so these are basically the big classes of groups which we know are Sopic, and then you can start combining them, and you have various operations under which this class of Sopic groups is closed. And yeah, but that's about it. I mean, there are not so many more groups which are known to be Sopic. Only some exceptional examples sometimes. And so that's basically what I wanted to say for today. And tomorrow, I think, or maybe Wednesday, I don't know, I will explain how a Sopic group, how one can show that the Sopic group actually satisfies this first conjecture. So the first conjecture can be proved for Sopic groups, and maybe I will also have time to say something about this second conjecture. Okay, thank you.